Professor Belfrost's computer science class is back!
Hi, and welcome back. Belfrost here, and today we'll continue on our lesson. Okay, so new week, new lesson. Okay, and today actually, previously we've done with explaining about anything related to control units and microprogramming, also hardwired implementation, and now we are moving to explaining another part of CPU, which is ALU, arithmetic and logic unit. But actually, arithmetic and logic both requires good understanding of mathematical concepts, operation on binary system, hexadecimal system, and many other number systems operation. So I think it's better to explain to you first about number systems, and then we will start to cover. Okay, we'll start to cover more on the main concepts of ALU operations. Okay, so great. We start with number system. So this is the first episode. This is the first video. I mean, the first lesson on number system. Don't worry if you don't understand this lesson well, because we'll have another lesson which is dedicated to revise you the concepts as well as give you some exercises. Okay. Okay. So yeah. Uh, let's review our last lesson first. Okay, so the implementation of microprogramming to create a control unit is that each microoperation will be represented by a different pattern of ones and zeros in a control word. So there are horizontal and vertical micro instructions. There are just two types. Okay, and set of micro instructions stored in the control memory. The control address register contains the address of the next micro instruction to be read. When a micro instruction is read from a control memory, it is transferred to a control buffer register (CBR). Reading a micro instruction from the control memory is the same as executing that micro instruction. Okay, and in Wilkes architecture, there are actually two main parts. The first part, the row, generates the control signals that control the operation of the processor, and the second part generates the errors of the row to be pulsed in the next machine cycle. Thus, each row of the matrix is one micro instruction, and the layout of the matrix is the control memory. Maybe this is just a recent concept, but actually it's better if you understand the picture, the figures I have given you in the last lesson. So please revise back. Okay, please replay the uh, last video to understand what actually this summary gives you. It tells you. Okay, so there are two concerns that involve in designing of micro instruction sequencing techniques. First, the size of the micro instruction, and second, the address generation time. There are three categories, broad categories based on the format of the address information. The microinstruction, first one is true address field, second is single address field, and third one is variable format. And there are various address in generation techniques which can be divided into first is explicit techniques, which is the address is explicitly available in the microinstruction, and second is implicit techniques in which require additional logic to generate the address. Microinstruction can be classified in several ways. For example, as we have told, as we have covered before, it's vertical, horizontal, unpack, hard, soft, microprogramming, and indirect encoding. And encoding is done in such a way as to aggregate functions or resources, so that the microprogrammer is viewing the processor at a higher and less detailed level. Good. Okay, we are done with the summary, the review of the last lesson, and move to today's discussion. Okay, so um, yeah, as I have told you before, that we need a good understanding of actually various type of number system, data representation, as well as data operation and Boolean logic. So we will first discuss that. Okay, so in everyday life, we use system based on decimal digits. We use decimal system, okay, decimal number system. Actually, we use and 10 symbols to represent anything, any operation that we are using in our daily life. So number 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so this is used to represent numbers, and yeah, this is the most common uh, number system that we use every day. But this is not the only number system. For computer system, we actually need another more suitable system, which is actually most of the computer system consists of binary digits, right? Okay, so often for computer system, binary numbers are used to describe the contents of computer memory, also the operation for the processor, and many more. At the other time, then decimal and hexadecimal numbers may be used too. Okay, mainly hexadecimal. Okay, and you must develop a certain fluency with these number formats, also how to do the conversion between one number format to another number format, so you can quickly translate numbers from one format to another. Okay, so each numbering format or system has a base. So what's a base? Okay, base is actually just representing the maximum number of symbols that can be assigned to a single digit. So hexadecimal numbers, for example, use the digits from 0 through 9 and continue with the letter A through F. Okay, you will see it in the next table to represent decimal values from 10 through 15. Okay, so it has in total 16. Okay, 16 symbols from 0 to 9 and A to F. Okay, to represent 10 to 15. I'm sorry. Okay, so it's quite common to use hexadecimal numbers when we're showing the contents of computer memory and uh, machine and instructions. Okay, for example, when we are doing memory addressing in assembly language later, that we'll use a hexadecimal number oftenly. Okay, maybe I will dedicate some videos to explain about assembly tutorial, but maybe I will not cover all assembly tutorial. And as there are actually many types of assembly, I will just use the 8886. Okay, the 8886 one. And maybe if you want to learn another assembly, you can do it. So you have MASM, TASM, and another kind of assembly. Okay, great. So please pay attention to the following table that shows the possible digits for the number system used most commonly in hardware and software manuals. So binary have we there is base 2 system. So there are only two possible digits, 0 and 1. For octal, there's 8, so 0 to 7. For decimal, there's 10, 0 to 9. And for hexadecimal, it's 16. We've covered it before, 0 to F. Okay. So first, let's start explaining from binary. So a computer stores instruction and data and memories collection of electronic charges. And representing these entities with numbers requires a system that geared to the concept of on and off, or true and false. Okay. So binary numbers is base 2 numbers, in which is binary digit called a bit. Actually, this is an abbreviation of binary digit, bit, okay, is either 0, 1. And bits are numbered sequentially starting at 0 on the right side and increasing toward the left. And the bit on the left is called the most significant bit, MSCB, this is short. And the bit on the right is called the least significant bit. The rightmost, I mean, okay, because if you left and right, which is left and right, okay, leftmost and rightmost. Okay, so leftmost one is MSB and rightmost one is LSB. Okay, great. So the MSB and LSB bit numbers, also the 16-bit number, binary number actually, is shown in the following figure. This is just example for you, okay? So for you to be able to properly identify which is MSB, which is LSB. So here's the example. Just pay attention. Okay, so binary integers. Okay, we start from integers. Actually, for any number system, we can describe any integer fraction. Okay, also integer and fraction together. Okay, but for today's discussion, we'll focus on integer. Okay, so binary integers can be signed or unsigned. So a signed integer is positive or negative, and an unsigned integer can only be positive. 0 is considered positive in most of computer calculation. Okay, so when writing down, I know that 0 is in mathematical is neutral, it's not positive nor negative, but in computer system we almost always assume that 0 is positive, so don't be confused with this thing. And also if in maybe when you are counting things, you're starting from 1, 2, 3, 4, 5, 6, 7, 8, and so on. But in computer, we are not doing indexing like that, okay? We are starting counting everything with zero, okay? Zero, 1, 2, 3, 4, and so forth, so forth, okay? So maybe these things sometimes will be quite boomerang, okay? It's quite confusing for a beginner, for novice, okay? But actually, you'll get used to after learning some lessons, okay? Great. Where I stop? Okay, okay. I find. Okay, so when writing down large binary numbers, many people like to insert a dot. Actually, I don't recommend this because you'll confuse it with a decimal point dot. But yeah, you can put a dot for your convenience. Okay, so you may insert a dot every 4 bits or 8 bits to make the number easier for you to read. For example, you can represent it as shown in the slide. Okay. Starting with the LS bit should be an unsigned binary integer represent an increasing power of 2, okay? Binary 2, base 2, okay? So the following figure contains an 8-bit binary number and showing how powers of 2 increase from right to left, okay? So we have from rightmost, we have to the power 2 raised to the power of 0, 2 raised to the power 1, 2, 3, 4, 5, 6, 7, okay? Because we only have 8 places here, okay? There is one bit, one binary digit is mostly 8, okay? If we are not dealing with parity, we are good with 8, okay? But if we are dedicated one bit for one position for parity, then it will be 9, okay? Great. So actually that's byte, okay? So 8 position in a row, that is a byte. One byte is 8 bits, okay? Maybe this will be another lessons topic, okay? And the table below lists the decimal values from 2 raised to the power of 0 through 2 raised to the power of 15, okay? So actually you don't need to memorize this because you can use calculator most of the time, but I suggest that you can do some kind of basic operation with on your head, okay? Not always counting on your calculator. Okay? So weighted positional notation represent a convenient way to calculate the decimal value of an unsigned binary integer having n digits, and that's the formula. Okay, so decimal equals to, yeah, actually just need to sum all of the product of the digits on each position with its suitable base raised to the power of the position or the index, okay? Where D in this case indicates a binary digit, okay? For example, okay, binary 00001 it is equal to 9. But how can we obtain this? Actually, you can calculate the value by leaving out terms equal to 0. Just take the 1, okay? So we have a position 2 raised to the 0, we have 1, and so the position of 2 raised to the power of 3, we have 1, okay? So just 1 times 2 raised to the power of 3, 2 cube, plus 1 times 2 raised to the power of 0, this is 1. So 8 plus 1 is 9, okay? Very easy. This is just basic. To translate an unsigned decimal integer into binary, then we must repeatedly divide the integer by 2, saving each remainder as a binary integer. And the following table will show you an example of how we do translating decimal 37, the decimal number 37 to the binary number, the suitable, the proper binary number, okay? So here you can see, so we keep dividing the integer by 2 until we reach the quotient of 0. So 37 divided by 2, 18 with 1, then 11. I'm sorry, 18 divided by 2 results in 9 with no remainder. Then 9 divided by 2, the quotient is 4 with 1 remainder, 1 as remainder. Remainder, I mean not reminder. Okay, so then we continue on. Okay, 4 divided by 2 it is 2 with no remainder. Okay, then 2 divided by 2 it will gives 1 as quotient and no remainder, and finally 1 divided by 2 it gives us quotient not 0 and remainder 1. Okay, then we rearrange it from bottom to top, not from top to bottom, but from bottom to top. Okay, so we can concatenate these binary bits as one string. Okay, from in reverse order, okay, to produce the binary, the converted binary, okay. So we have 100 101. Done. Because computer storage always consists of binary numbers where lengths are multiples of 8, then we can fill the remainder 2-digit position on the left with 0. But this is not a must. If you want to do that, I'm very happy. I'm very glad. Okay. There's a simple formula actually to find how many binary bits you need to represent for the unsigned decimal value n. So it is b equals, this is the formula, ceiling log base 2 n. So you have log base to n. So you say you have n equals 17, that's the decimal number, I mean, that you want to convert to binary. Then log base to 17 equals to 4 times, 4 times, 4 point blah blah blah. But you need to just round it up to make 5. So you need 5 bits to represent 17. Done. Easy. Okay, so when adding two binary integers, we should proceed bit by bit, starting with the low order pair at bits of bits, which is on the rightmost position, and adding subsequent pair of bits. And there are four ways to add two binary digits. So 0 plus 0 will make 1, will make 1, and 0 plus will makes 1. 0 plus 1 makes 1, I mean, 1 plus 0 makes 1, 2, and 1 plus 1 makes 1, 0. This is not 10, okay? I always emphasize that every number system has their own dedicated way to how it is read. Okay, so this is not 10. Okay, for binary number, we should never, okay, for binary system, we should never use any decimal way to represent any number. Okay, so you read one by one. Okay, for example, we have 100, not 100. Okay, you have 110, not 110. Okay, so this is 10. It means 0 for the lowest position and 1 for the next highest position. Okay, great. So you pay attention. You have watched before that when we add 1 plus 1, 1 and 1, 1 to 1. Okay, so the result is 10. Actually, not 10, 10 binary, and actually this equals to decimal value of 2. Okay, because 0 times 2 raised to the power of 0 plus 1 times 2 raised to the power of 1, it results in 2, right? Okay, so the extra digit generates a carry. Okay, so 1 in this case actually is called carry to the next highest bit position. Okay, and first time it is 0, but because it also have a carry with it, that it will be 1. Okay, here is how to add, for example, binary 000001000 to 000000111. Here's that example. Okay, this is not the question that will appears in your exam paper. Okay, but this is just example. Okay, so yeah, uh let's analyze the figures. So beginning with the lowest bit, okay, so we add 0 and 1, it's 1. Then same happens with 0 plus 1, the 1. But 1 plus 1, the third position from right, it will result in 1 0. Then the 1 will be carried to the fourth position, and we add 0 0, this 0, but we have to carry, so we add the 1, so it results in 1. And then the fifth position 0 0 0 0 0 0. The seventh position also 0 0 0. The eighth position from the right is also 0 0, which also gives us 0. So the final result is 0 0 0 1 0 1 1. Okay, which equals to 11. Okay, so because 2 raised to the power 3 plus 2 raised to the power 1 2 raised to, plus 2 raised to the power of 1 0, I mean. Okay, so 8 plus 2 plus 1, that is 11 for the decimal value, I mean. Sometimes a carry is generated out of the high speed position. And when that happens, then the size of the storage area set aside become very important. And if we add 1111111 to 000000001, for example, that A1 carries out of the highest bit position and the lowest 8 bit of the sum equals all zeros. And if the storage location for the sum is at least 9 bits long, then we can represent the sum as 1000000000. But if the sum can only store 8 bits, then we will lose the one. And this is very critical, okay? This is very critical when you have a very important information but you lost it because you have no adequate storage, okay? You only have 8 bits while you should represent this number with 9 bits, and this is terrible, okay? You will only store 000000000 when you should, okay? On the other hand, store 1000000000, okay? So only the lowest 8 bits will remain. Okay, so you need to consider this. Actually, every time you do any operation, you should always consider this, okay? So the basic storage unit for all data in a x86 computer is a byte that contains 8 bits, as I have told you before. And our storage size are words with 2 bytes, double word 4 bytes, and quad words 8 bytes. Okay, this is shown in the figure. Okay, so a number of last measurement are used when referring to both memory and disk space. So we have kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte. Actually, you maybe I don't think that you need to memorize all this term. Okay, this is just a physics term. Okay, this is just the prefix you use in physics. Okay, to indicate actually you raise the exponent to what number, but maybe the most prefix that you will encounter is this kilo, mega, giga, and tera, and peta maybe, but maybe for exa, zeta, yotta you'll rarely see. So it's okay if you don't know. Large binary numbers are actually cumbersome to read, to read, to be read, I mean. So hexadecimal will offer a convenient way to represent the binary data. With each hexadecimal digit, it represents 4 binary bits, and 2 hexadecimal digits together represent a byte. So a single hexadecimal digit represents decimal from 0 to 15, so letters A to F represent decimal values in the range of 10 through 15. Here's the table, showing the sequence of 4 binary bits that translates into decimal or hexadecimal. Okay. Maybe it's necessary for you to take a capture, take screenshot on this one if you want. Okay. Okay, so here's the example for you to show how actually you can convert a binary 0001, 0110, 0110, 0111, 1001, 0100 is equivalent to the hexadecimal form, which is 16A794. Okay, so actually it looks like code name, okay, but actually, yeah, this is computer stuff. Okay. So yeah, it has been grouped into 4 so it's very easy for you to done it. You just convert it to the suitable hexadecimal. Okay, for the leftmost group, okay, we have 001 is equals to 1. We have 0110 is equals to 6. Then 1010 is equals to 10, which is A. Okay, it hexadecimal representation. Then we have 111, it is 7 in hexadecimal representation. When 1001 it is equals to 9 and 0100 is 4. Okay, very easy done. So 16A794. So in hexadecimal, each digit position represents a power of 16. Okay, because we work with hexadecimal. And this is helpful when calculating the decimal value of a hexadecimal integer. Suppose we number the digits in a 4-digit hexadecimal integer with subscript of D3, D2, D1, D0, then the following formula can calculate the integer's decimal value. And actually, we can generalize this formula for any n-digit hexadecimal integer, as shown. By understanding this, then you can also generalize a more general formula for any n-digit integer in any base b to convert it to decimal using the following formula shown in the slide. Maybe you want to capture this one. Okay, so for example, hexadecimal 1234 equals to 1 times 16 cubed plus 2 times 16 square plus 3 times 16 raised to the power 1 and 4 times 16 raised to the power 0. So it has the decimal equivalent of 4660, okay, 4660. Whew. Similarly, hexadecimal 3BA4 is equal to 3 times 16 cubed plus 11 times 16 square plus 10 times 16 raised to the power 1 and 4 times 16 raised to the power and 0. Or it equals the decimal 5, I'm sorry, 15,268. Okay, so the following figures show how to do this conversion. Okay, just need to do it step by step. Okay, and here's the table listing powers of 16 from 16 raise to the power of 0 through 6 raise to the power of 7. Actually, you don't need this actually, maybe. You can just use calculator. Maybe calculator is your best way for doing any calculation related to, yeah, computer science. Okay, so to convert an unsigned decimal integer to hexadecimal, you just need to repeatedly divide the decimal value by 16 and retain its remainder as a hexadecimal digit. Actually, you have done this before, right? With binary, and the formula is same. You just need to repeatedly divide the decimal value with the base. Okay, so for binary, you divide it with 2, and for hexadecimal, you divide it by 16. And if you are doing operation 6 of octal number system later, then you just need to repeatedly divide it with, okay, or by 8. Okay, for example, say that you have this problem, this yeah question. Okay, so you need to convert decimal 422 to hexadecimal. So yeah, repeatedly do the division. So 42 divided by 16, you have 26 with remainder 6. And then 36 divided by 16, you have quotient 1, remainder 10, which is equal to A. And 1 divided by 16, the quotient 0, and the remainder is 1. So the resulting hexadecimal number is read from bottom to left. Bottom to top. I've repeatedly tell you, from bottom to top. Okay? So we have 1A6 done. And how to convert from decimal into some other number base? Then you just need to replace the divisor, as I've told you before, with the desired number base. Okay, so debugging utility programs usually display memory addresses in hexadecimal, and it is often necessary to add two addresses in order to locate new address. Unfortunately, hexadecimal addition was the same as decimal addition, and if you just change the number base, okay, yeah, suppose that we want to add two numbers, say x and y, using numbering base b. I will number the digits from the lowest position x0 to the highest. And if we add digits xi and yi in x and y, so we can produce the value si. And if si is greater than or equals b, then we just recalculate si is si mod b, okay, modulus, this is modulus operation, the remainder operation, and generate a carry value of 1. And when we move to the next pair of digit, xi plus 1 and yn plus 1, we just need to add a carry value to the sum. For example, the addition of, yeah, 6a2 and 6 and 49a. In the lowest digit position, so 2 plus a equals 12. And yeah, then the next position, a plus 9 is 19. And there is a carry because of the number carry of 1 with because of the number base. So we calculate 19.16, which is 3, and carry a 1 to the third digit position. Then we add 1 with 6, which is uh, decimal 1 plus 6 plus 4, which is decimal 11. Okay, and we have the decimal sum B3C. Okay, now let's continue our lesson on signed integers. So signed binary integers are positive or negative. So yeah, you can see for the x86 processor, then the MSB indicates the sign. 0 is positive and 1 is negative. Okay, you can see it as shown in the figure. So we can just negative integer by using the two complement representation, okay, or it means that if you add the number to its additive inverse, then the sum is 0. Okay, So tools complement representation is useful to processor designers because it will remove the need for separate digital circuit to handle both addition and subtraction. Okay. So for example, a minus b is actually just equals to a plus negative b. And the two complement of binary integer is formed by inverting or complementing its bits and adding 1. Using the 8-bit binary values, for example, its two complement turns out to be as shown. As can be seen as follows. I want you to learn it by yourself. We will discuss this more in the next lesson. Okay. Also for this, I want you to pay attention first. I'll not explain because I will explain it in depth in the next lesson. Actually, this is next lesson material. I'll tell you more next lesson. Okay, so here's the example. Okay, I'm in a little hurry, so I want you to take screenshot it first. Okay, and learn it by yourself. Okay, after learning this, then I want you to do your assignment. Only two problems, and solve it by yourself. After this, check it with this solution given, and done. We are done with today. So here's a little quote for you. So Leo Tolstoy once said, "True life is life when tiny changes occur." So thank you for watching, and subscribe, give a like, comment, share this video, and I'll be back on every Monday. And please visit my website sciencewithxysd.unux.com. Keep watching and be thoughtful. Goodbye. See you.